So we're looking at section 4.3, which is about primes and greatest common divisors. There's quite a bit more that goes into this section, but it's entitled Primes and Greatest Common Divisors, and these are some of the big themes that show up in this section. So we want to begin with a definition of what a prime is. So in this class, in this course, we're going to only consider positive primes. We're not going to think about negative primes. So from a algebraic perspective, you can look at something called negative primes, but we're looking more at number theory in this class, and primarily we only consider the positive primes. So a positive integer p is said to be prime provided two things happen. Number one, p is bigger than 1, so prime has to be bigger than 1, and the only positive factors are 1 and p itself. So there are two things that go with being prime here. You have to be bigger than 1, and your only positive factors are 1 and yourself. Okay. Now let's look at some examples of primes. So starting with the smallest prime, so 1 is not a prime, right? 1 is not a prime. Definition says it has to be bigger than 1. So the first prime would be 2, right? 2 is bigger than 1, and the only positive factors of 2 are 1 and 2 itself. 3 would be a prime, right? It's bigger than 1, and the only positive factors are 1 and 3 itself. 4 is not, 5 is. 6 is not, 7 is. 8 is not, 9 is not, 10 is not, 11 is. You can have 13, 17, 23, 29, 31, 7, 41, and I'll stop at 47, and so on. You can keep going. It turns out that there are infinitely many primes. That's a fact. That was proven by Euclid of Alexandria, I believe sometime around 200 BC. So a theorem by Euclid. There are infinitely many primes. That means the primes go on forever. And a really big exercise in mathematics is when supercomputers are running constantly looking for the next prime number. That's something that mathematicians are interested in for practical reasons in cryptography. What's the next prime number? So they have prime numbers out there with lots and lots of digits, probably millions or even billions of digits, I'm not sure. And they're looking for the next prime number. What is the next prime number? Okay, so what does it mean to not be prime? Here's a definition. A positive integer n is composite. That's what we're going to define here. A positive integer n is composite. We're defining composite provided it is not prime. Positive integer n bigger than 1. Let's say bigger than 1. So a positive integer n greater than 1 is composite, provided it is not prime. So it still has to be bigger than 1 to be composite. It has to be a positive integer. But if it's not prime, that means it would have positive factors besides 1 and p. Positive factors besides 1 and p. So here's a fact about a composite. And a positive integer n that's greater than 1 is composite precisely when, that we'll say if and only if, that means precisely when n has a factor A, let's call the factor A, with A greater than 1 and less than n. So a positive integer greater than 1 is composite precisely when it has a factor between 1 and n. So it's not equal to 1, it's not equal to n, it's in between there. Greater than 1 and less than n. That factor we're calling it. Okay, so exercises. Now let's just say examples, I guess. One, 4 is composite since it breaks up into factors 2 times 2. So it has factors besides 1 and 4, right? 2 times 2. What else? 6 is composite since it has factors 6 equals 2 times 3, right? It has these factors which are neither 1 nor 6. Yep. Okay, so let's move on to what's called the fundamental theorem of arithmetic. The fundamental theorem of arithmetic. So arithmetic, when you hear the word arithmetic, you often think like addition, subtraction, multiplication, division. But actually arithmetic, if you go back and look at the history of the meaning of this word, arithmetic actually means number theory. Number theory is a field of mathematics where you study the integers. So basically this is the fundamental theorem of number theory. Now every field of mathematics has a fundamental theorem. You have something in calculus called the fundamental theorem of calculus, which relates integration and differentiation. In algebra, you have a fundamental theorem of algebra, which tells you that pretty much every polynomial factors into n. If it's a nth degree polynomial, it factors into n factors, where those factors can have complex roots. So in number theory, we're going to do the strong version of the fundamental theorem of arithmetic. There are different versions of the fundamental theorem of arithmetic, but we're going to do a strong version, and we'll state it this way. If n greater than 1 is a positive integer, then n can be written in the form p1 to the alpha 1, p2 to the alpha 2, p3 to the alpha 3, dot, 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 pk to the alpha k, where p1 is less than p2 is less than p3, and so on and so forth, is less than pk. These pi's are primes. We'll say distinct primes. And the alpha i's, alpha 1, alpha 2, alpha 3, and so on and so forth, through alpha k, we'll call those the alpha i's. The alpha i's are positive integers. So essentially what this is telling us is that if you take any positive integer that's greater than 1, you can break it up into a product of primes that have exponents. So this is called the prime power factorization. So it's basically saying that every positive integer greater than 1 has a unique prime power factorization. So let's do some examples of prime power factorizations just to get used to this. Examples. Write the prime power factorization of each positive integer. Number 1, I have the number 54. This is my n, 54. So if we do a factor tree here on the side, 54 is even because it ends in an even digit. So you can divide it by 2, or you say it has 2 as a factor. 2 is prime, so I'll circle that. 54 divided by 2 is 27, so 27 is a factor. You could break 27 up into primes, and that 3 times 9. 3 is a prime, and then 9 you break up into 3 times 3. So I'm circling my primes. You say 54 is what? 2 times 3 cubed, right? You have 3 copies of 3. 1, 2, 3. So it's 3 to the third power. So there we have it. We have 2 times 3 cubed. That's our prime power factorization here. So basically the P1 here is 2. Alpha 1 is 1. P2 is 3. And alpha 2 is 3. All right, let's do another one. Let's say we have 324 as our positive integer, and we want to factor that down. So off to the side, I'm going to do my scratch work, my factor tree. 324. Now, let me tell you a trick to show something is, well, okay, never mind. I'll just start factoring. I know 324 is even. Anything that's even is going to have a even digit on the end, so 324 is divisible by 2. Circle that. So 324 divided by 2, I believe, is 162. 162 is even because it ends in a 2. So 2 is going to be a factor of 162. 162 divided by 2 is 81. We know 81 breaks up into 9 times 9. And 9 breaks up into 3 times 3. And the other 9 will break up into 3 times 3. So basically my prime power factorization here is 2 squared times 3 to the 1, 2, 3, 4. Right, I have 2 copies of 2 and 4 copies of 3. All right, let's do a number 3. Number 3, we have 175. Uh, 175, okay, I'm going to erase my scratch work here. 175, doing a factor tree, has a digit of 5 on the end. Anytime you end in a 5 or a 0 on the end, you're divisible by 5. So 5 is a factor. When I divide 175 by 5, I get 35. So 5 is prime, and 35 breaks up into 5 times 7. So here I have, let's see, for my prime factorization, I'm going to have, this won't work, 5 squared times 7, right? You have 2 copies of 5 and 1 copy of 7. So here my P1 is actually 5, my alpha 1 is 2, and my P2 is 7, and my alpha 2 is 1. Okay, one more, 4. We have 531. Now, I'm not quite sure off the top of my head, just looking at that, just inspecting it, what I could factor that by. But I know a trick. Here's an important fact. I'm going to write this down below this problem. A positive integer, n, greater than 1, is divisible by 3 if and only if three divides the sum of its digits. The sum of the digits of n. Now what that means exactly is I can take, in this case, 5 plus 3 plus 1, right? These are the digits of 531. And when I add those up, I get 9. Now we know 3 is a factor of 9, right? 9 is divisible by 3, or 3 divides 9, different ways to say that. So that means 3 would also have to divide 531. So I'm going to take 531, and I know 3 divides it. So what's 531 divided by 3? Let's see. 531 divided by 3, using my calculator, gives me 177. We know 3 is prime. Now, how about 177? Well, if you do 177, 1 plus 7 plus 7, that's 15. 3 divides 15. So 177 is divisible by 3. So I'm going to do a factor of 3. What's 177 divided by 3? It's going to be 59. And 59 is a prime. That is indeed a prime. I don't think I had it in my list of primes. I didn't get that far. I only went up to 47, but yeah, it's a prime. So 531 is going to factor into 3 times 3 times 59, or 3 squared times 59. All right, so this is all I'm going to do in this first video. Getting up the prime power factorizations, the fundamental theorem of arithmetic. So in the next video, we will continue looking at primes and prime factorizations.